video, we will just see how to define a path in the complex plane as well as a kind of introduction to before we define Mobius transformations. So the first definition is of path. A path in a region G subset of C, a region is an open connected set inside the complex plane, is a continuous function called gamma, say it is gamma, from a closed interval AB inside R into G. So, in order to understand it better, let's see it as an illustration. So here we are having the real line R, and in the real line we are having a closed interval AB, and gamma is a function from this domain closed interval AB to some region G, which is given as the dotted boundary here inside the complex plane here. Okay, so this gamma, when it is mapped, you are going to get something like a continuous curve that is called a path. So this A will be mapped by this gamma. You will have gamma of A to be the first point of this path, and the next point inside will be mapped to the next point on this path, and it is continuously mapped every point in this domain, and the last point is B, and that will be mapped to gamma of B, which is the terminal point of the path. That's how a path is inside the complex plane, and that's how it is defined. And the next definition is what is a smooth path. So for a smooth path, basically we need a continuous function gamma from closed interval AB to G, and also if gamma dash of t, that is gamma of t is necessarily a function, and its derivative should exist for every t inside the domain, and the derivative function, the derivative we are getting, should be continuous. Then we call gamma to be a smooth path. The next thing is how we define a piecewise smooth path. For that, what we have to do is partition the domain into n subintervals. That is, suppose if A is equal to T naught, so and the next point of subdivision is T1, that means the first subinterval is T naught T1, and the next subinterval will be T1 T2, etc. The last subinterval will be Tn minus 1 Tn, where Tn is equal to B. And in each of these closed subintervals, gamma will behave as a smooth path on each of the subinterval. And then we call gamma to be a piecewise smooth curve. That means the path is being smooth in each of its piece, right? And the next definition or the term we are coming across is when does a path gamma from closed interval AB to C has a derivative gamma dash of t. What does it mean? We said that here this gamma dash of t exists. So here it just means that limit of h tends to 0 gamma of t plus h minus gamma of t divided by h exists, and we call when it exists it as the derivative of gamma at t, gamma dash of t, for every a is strictly less than t is strictly less than b, and also that the right and the left hand side limits exist for t is equal to a and t is equal to b respectively. That's how we define the derivative usually. So that is the same here for this function too. And the next concept we have to look forward to is, suppose if we have a smooth path gamma from closed interval AB to the region G, and suppose if there is some T naught in open interval AB such that at T naught the derivative is not equal to 0, then we can say that our path gamma has a tangent line at the point gamma of T naught, and we are calling it as Z naught. Gamma of T naught is equal to Z naught. And we have to note that this line will start from the point Z naught, that is gamma of T naught, on the path in the direction of the vector gamma dash of T naught, and the slope of this line will be defined as the tangent of the argument of gamma dash of T naught. And also the next segment we are dealing with is how to define an angle between two paths. So suppose, especially the smooth paths, we are talking about smooth paths now. If gamma 1 and gamma 2 are two smooth paths, and suppose both of them are intersecting at some point set naught, definitely that set naught will be some point in gamma 1 as well as gamma 2, right? So the parameter we are taking it as t1 and t2 for gamma 1 and gamma 2 respectively, that is gamma 1 of t1 is equal to gamma 2 of t2 is equal to set naught. And suppose if at both the points t1 and t2 the derivative of gamma 1 and gamma 2 is not equal to 0, then we can define an angle between the paths gamma 1 and gamma 2 at the point set naught, and that is defined as the argument of gamma 2 dash of T2 minus argument of gamma 1 dash of T1. So that is an important definition we require. And in the next session, we are going to prove the theorem 3.4, which will be the next lecture video. So keep on reading this intro part so that you become familiar with all those concepts about smooth paths, what is the angle between two smooth paths, and so on. So thank you for listening to this small video. See you in the next video lecture.